Hello, this is FASTECH. Today's subject is the stepping motor. It is possible to have a better performance than AC Servo? Until now, it has been taken for granted that AC Servo's performance is superior to stepping motor. However, AC Servo raises the position accuracy of stepping motors through high precision encoders and takes advantage of the characteristic of stepping motors that AC Servos cannot have, allowing them to have the same or better performance as AC Servos in some applications. I will explain in detail now. First of all, I will explain how the position of AC servo and stepping motor is formed in the current Korean market through market segmentation. This is the data only for Korean market. The horizontal axis is performance and vertical axis is cost. Existing open-loop stepping motors were recognized as low cost and low performance, and the AC servo is a high performance, high cost motor, and the location of the closed loop stepping motor was here. It is common perception of customers that it is better in performance than open loop stepping motor and lower than servos motors. In this market, competitors' closed loop stepping motor has been dominating the Korean market for 15 years at twice the price of AC servos with two advantages: no hunting and shorter settling time. In addition to these two advantages, FASTECH moved the market from here to here with another advantage, high position accuracy, and achieved that #1 market share in Korean stepping motor market. From now on, let's compare these three advantages: no hunting, short settling time, and position accuracy between AC servo and AC servo with laser demo. The terms to compare are position accuracy and lost motion related to position accuracy, comparison of settling time according to overshoot and overshoot related to short settling time, and robustness related to no hunting. We have prepared demo jig to compare the two motors in these 5 aspects and see the difference in performance. First, let me explain the specification of the demo. As you can see, there is a demonstration in which you can visually observe the movement of the motor shaft by attaching a mirror to the motor shaft and reflecting the laser pointer on the screen. The measurement conditions for both motors are the same. The size of AC servo is 42 mm and the resolution of the installed encoder is 10,000 ppr. The capacity of the AC servo is 100 watt and the resolution is also set to 10,000 ppr. The distance between the demo and the wall is 8.4 meters. First, let's compare the position accuracy of two motors. As mentioned earlier, the measurement conditions for both motors are the same. Both motors were made to move at equal intervals by 0.36 degrees in only one direction. At this time, let's compare whether the actual position comes the same. As you can see, the AC servo has a constant moving distance at equal intervals, so it has high position accuracy without any position error. One thing to note is the AC servo. Even though it is a stepping motor, you can see that it has the same high position accuracy as an AC servo. High position accuracy means that when it is moved in one direction, it does not show position error like AC Servo and EC Servo. Next, let's compare the lost motion. The measurement conditions were the same as before. The difference from position accuracy we saw earlier is that the motor rotates alternately in the clockwise and counterclockwise directions by 360 degrees. That is, in the case of lost motion, the direction has to be changed. As you can see, the AC servo rotates 360 degrees regardless of the direction, and it returns to the target position without any position error. Likewise, even if the direction of the AC servo is changed, you can see that it returns to the target position without any position error. Lost motion refers to the position error that occurs when the direction changes. In summary, position accuracy and lost motion are related only to accuracy of the encoder, and AC Servo uses a high precision encoder like AC Servo, so it always checks the current actual position and corrects it, so that there is no position error. Thus, AC Servo has high position accuracy and small lost motion. Next, I'll show you the overshoot. Overshoot means the value of how far the motor has exceeded the target position. The demo used the same demo as before. From now on, let's see how the overshoot differs when the motors are moved under these conditions. As you can see, EC Servo has a small overshoot, but AC Servo has a relatively large overshoot. Of course, the AC Servo used in the demo is not optimal because it has been tuned with the auto-tuning function, and overshoot can be reduced if it goes through a precise tuning process. But even without such a hassle, AC Servo can show its performance without overshoot. This overshoot will affect the settling time. I'll show the difference in settling time according to the overshoot in a video. I set the input value to 0, which is conditioned that the next command is executed only when the commanded position is reached without an error of 1 pulse, and repeated operation 50 times without waiting time between commands. As you can see, EC Servo with less overshoot completed 50 repetitions about 4 seconds before AC Servo. If the larger overshoot occurs, more time is required to execute the next command. In other words, the takt time would increase. That is why short settling times are important. Finally, let's compare robustness. Let me show you what happens when the same external force is applied to the mirror on both motors. EC Servo does not move much even when external force is applied, whereas AC Servo shakes greatly, that is, hunting occurs. This will be explained in more detail through a comparison of the torque characteristic of AC Servo and EC Servo and a demo video later. Before that, I would like to ask you a question with a leader machine as an example. This application is the XY Zeta vision alignment stage, one of the most common applications. Basically, alignment is the machine that allows the camera to accurately capture the object to be inspected by continuously moving a short distance. In this machine, a 100-watt AC servo is mounted on the right, and an AC servo of the same size is mounted on the left. Would AC servo be better for this application, or AC servo be better? Customers have taken it for granted to use AC servo in application requiring high position accuracy. As mentioned earlier in the market segmentation, customers generally have a perception that AC servo performance is better than stepping motor. Of course, the correct answer is AC servo. But the why is important. How can a stepping motor show better performance than an AC servo? We will explain it in the next chapter. First, I will explain the difference between AC servo and stepping motor with torque comparison. Let's compare the torque of similar size AC servo and stepping motor. The graph shown above is the torque graph of 200-watt AC servo, and the graph below is the torque graph of AC servo of the same size as 56 large. First, AC servo motor have two kinds of torque, a latent torque and an instantaneous torque, which is 3 times higher than the rated torque. On the other hand, step motors have a holding torque, not the rated and instantaneous torque, that gives maximum torque when the speed is 0. That is, when the motor is stopped at the target position. Simplifying this, the rated torque of the AC servo is 1, the instantaneous torque is 3, and the holding torque of the stepping motor can be 2. Even if this is applied compared to the 100-watt class of servo and 42mm stepping motor of similar size, the torque value would be different, but the ratio of rated torque, holding torque, and instantaneous torque is always the same as 1, 2, 3. An AC servo has higher torque than a stepping motor because of this instantaneous torque of 3. Since the instantaneous torque of the AC servo is 3 and the holding torque of the stepping motor is 2, the torque of the stepping motor is smaller than the servo. But the important thing here is that the instantaneous torque is not always useful torque. There is limitation. If this instantaneous torque of 3 is always used, overcurrent and overload alarm are likely to occur in the AC servo drive. For example, if you perform rapid acceleration, deceleration using instantaneous torque of 3, the torque is proportional to the current, so if you use this torque for a long time, the coil inside the motor may burn out. It triggers an alarm, etc. This instantaneous torque can be used only for a while during acceleration and deceleration. Also, even if an instantaneous torque of 3 can be used when the speed is 0, which means it is in the target position, the stepping motor has a higher torque than the AC servo because of the holding torque of 2. As previously explained, the instantaneous torque of 3 is not always used, but the torque of the AC servo motor is proportional to the position error. The smaller the position error, and the smaller the torque, and the smallest torque at stop, that is at the target position. For example, as you saw in the robustness comparison video using the laser video earlier, when a small mirror is attached to the motor shaft and touched by hand, the torque generated by the AC servo is very small because the position error is small. Therefore, it is easy to rotate the mirror by hand at first, but as the mirror is rotated more and more, the position error becomes larger, and the AC servo supplies more current to the drive to reduce this position error. Thus, it becomes difficult to rotate the mirror. In other words, the torque of the AC servo motor is not always an instantaneous torque of 3, but is proportional to the position error and produce the smallest torque when it is at the target position. So there is a high possibility of hunting after stopping. Of course, if the gain is adjusted for the AC servo, the response improves, as you can see, but when it is near the target position, you can see that the torque is the same regardless of the gain. On the other hand, since the torque of stepping motor is not proportional to the position error, it is only related to the speed and has a holding torque that produces the maximum torque when stopped. The possibility of hunting after stop is smaller than that of AC servo. Now let's divide the motion into two and compare it. One is a long pitch motion in which there is a constant velocity section, and the other is a short pitch motion then decelerated immediately after acceleration. Now let's assume that a certain load is accelerated and decelerated by A using the instantaneous torque of 3 of the AC servo. Assuming that F equals MA, M, the load, is a fixed value. First, in the case of long pitch motion, acceleration is A when accelerating. Since there is no change in speed in the constant speed section, the acceleration of the load is 0, and the acceleration when decelerating is minus A. Therefore, the absolute value of acceleration deceleration applied to the load, that is, the impulses F, is A. On the other hand, in the case of short pitch motion, the constant velocity section does not exist, and deceleration is performed immediately after acceleration. In other words, since acceleration and deceleration change continuously, the amount of impulse applied to the load is 2A. To make it easier to understand, for example, if you use an instantaneous torque of 3 like an AC servo, you can understand that the shock transmitted to the mechanical body is doubled if you press the accelerator and brake continuously. Therefore, in short pitch motion, instantaneous torque of 3, that is maximum torque of AC servo, cannot be used. This is because in case of short pitch motion, there is a possibility of shock or vibration of the mechanical system depending on the load if using instantaneous torque 3, because the acceleration is large. Such as a car as an example. In order to reduce the shock or vibration of the mechanical system, the acceleration must be reduced. But to reduce this acceleration, the acceleration deceleration time must be increased. This reduces the acceleration received by the load, and if the torque drops to the point where it can accelerate with the torque of 2, not 3, which is holding torque of the step. Even if the AC servo has a maximum torque of 3, it cannot use this torque. And in this case, the AC servo, stepping motor, and torque become the same, and the acceleration capability is also the same. Back to the beginning, I will ask you again. In short pitch motion application that move short distance at high speed, such as the XY zeta alignment stage, when it is stopped at the target position and shock or vibration comes from outside, Which motor of AC servo or stepping motor is likely to hunting? It is an AC servo. As mentioned earlier, if you use the instantaneous torque of 3 of the AC servo, it can give a shock to the mechanical system when aligning. Also, when aligning, the distance is very short, so it is often difficult to use an instantaneous torque of 3. First of all, as you saw in the video comparing the robustness of the laser demo, the AC servo generates the smallest torque when the target position, that is, when the speed is 0, so there is a high possibility of hunting after stopping. However, in the case of stepping motor, there is a holding torque that the greatest torque at the target position, so when the alignment is over, it stops at the target position and holds the stage tightly with the holding torque. This is demonstration of the difference between AC servo and AC servo in the high-speed short-pitch motion described so far. The same actuator with the belt structure is installed with the 42mm size AC servo on the left and a 100-watt class AC servo on the right. There is a camera on each side and there is a piece of paper with a small word on it, as the camera moves by motor continuously over a short distance that captures the written text. You can think of it as the same as a vision inspector. As you can see, the AC servo has a high holding torque and less hunting when stopped, so the text is captured by the camera even in a short pitch motion. Since the AC servo generates the minimum torque when stopped, hunting occurs. And you can see that the AC servo cannot capture a text in a short pitch motion. With AC servo, you can see the text only when you move the beginning and end. That means a long pitch. To explain more about the belt pulley system, due to the mechanism structure, the belt pulley is a short pitch motion from the motor shaft perspective. For example, in the case of a ball screw, when the lead is 10mm, the motor moves only 10mm in one turn. But in case of the belt pulley, when the radius is 10mm, when the motor turns once, the belt moves 62.8mm, as you can see. I will show you a demonstration of the belt pulley in action. If you look at this part, you can see the short pitch motion of the motor in the belt pulley demo. You can see the word no hunting is accurately captured without hunting even in a short pitch motion. In summary, in case of an AC servo, the position error decreases when decelerating from the target position, and the motor torque decreases when the position error is decreased. Near the target position, the torque generated by the AC servo is very small, and the belt is low rigidity, so when the belt is shaking, the force is transmitted directly to the motor shaft, so it continuously affects the shaft. On the other hand, in case of a stepping motor, as the speed decreases, the stepping motor increases the torque and produces a maximum torque near the speed 0, near the target position. So, in the case of AC servo, since the torque is small near the target position, it is difficult to stop without hunting because the vibration caused by the tension of the belt is directly transmitted to the motor shaft. The stepping motor can overcome the vibration and stop without hunting without a gearbox because the torque generated by the stepping motor at the time is relatively larger than that of the AC servo, even when the vibration caused by the belt tension is transmitted. So in worst case, AC Servo needs to attach gearbox. So I show you a video of the vapor transport robot as an example. As you can see, the vapor transport robot has a belt-to-pulley structure inside. In the case of belt drive, the moving distance is long, so many people think that it's a long pitch motion that moves a large distance from a motor standpoint. However, from the motor standpoint, it is a short pitch motion due to its mechanical structure. As you can see, the distance its object moves seems to be long, but you can see that the motor does not turn even a single turn. This is an example showing that the step motor can be applied to such a vapor transport robot. Here is a Delta robot demo. In general, AC servo motors were used a lot for Delta robots. However, as you can see, the Delta robot is a short pitch motion with a short movement due to its mechanical structure. In this case, if a servo motor is used, the torque at stop is small and the possibility of hunting is high. So most of the motor shafts are attached with a gearbox. On the other hand, in the case of a stepping motor, it generates the largest torque when stopped. So as you can see, it is possible to driven a Delta robot without a gearbox. In the other words, it is an application in which the advantages of a stepping motor can be applied in the case of a Delta robot. This is a demonstration of a Delta robot from Aarhus, Germany. This Delta robot has a belt-to-pulley structure and it is a short pitch motion from the perspective of the motor shaft due to its structure. You can see that the motor does not rotate 180 degrees. The stepping motor does not need a gearbox because it has high holding torque when it is operated in a low speed range with short pitch motion. If you use an AC servo here, you may need to attach a gearbox when stopping. The following is a demo showing a high-speed short-pitch motion using two motors. A disc with 8 small grooves was attached to the two motor shaft, and the grooves were vertically engaged. You can see the grooves interlock without collision, while the two motors alternately driving in high-speed, short-pitch motion. This operation is possible because of the precise position control through the high-resolution encoder of the AC Servo and the characteristic of the step motor without hunting after stopping. Let's summarize what we have looked at so far. FASTECH AC Servo has 3 advantages by adding high position accuracy to the 2 factors that it can reduce the settling time due to high holding torque characteristic of the stepping motor, so there is no hunting after stopping and there is less overshoot than the AC servo. In the Korean market, it was possible for FASTECH to move the closed loop stepping motor market here. It also replaced the AC servo market, especially 100 watt and 200 watt class AC servos. It wasn't easy. This is because customers' perception of AC servos and stepping motor was so strong. However, after the customer felt or actually experienced the advantage of AC servo, it was possible to replace it. And now many customers use AC servo. From now on, I will introduce the actual application example of AC Servo. Prior to introducing application examples, the main factors that could be applied to AC Servo are as follows: position accuracy, lost motion, overshoot, and robustness. High position accuracy, small lost motion, small overshoot, robustness is stop at the target position without hunting after stopping. Based on these four factors, I will now introduce how AC Servo could be applied to each application by replacing AC Servo. The following is the LC dispensing machine. LC means liquid crystal. Two glasses are needed to make LCD panels used for this TV and monitor. It is the TFT panel on the left and the color filter on the right. A certain amount of liquid crystal is dropped on the TFT panel as shown in the picture. Glue is applied to the color filter as shown in the picture. And then the part where the liquid crystal is dropped on this panel is bonded to color filter on the right. When bonded together, the TFT is in this part, the color filter is this part, and this is the glue, and this red part is the liquid crystal. And when it is bonded, the liquid crystal spread quickly. For example, when you press the panel with your hands on the TV, that is when you pressed the liquid crystal, the pressed part is changed color. The reason to change color is that the liquid crystal is liquid, so when it is pressed, the liquid crystal escaped to the other side and the amount of liquid crystal changes in the pressed part, causing the color to change. For this liquid crystal volume to be constant, this drop must be constant. In other words, it is very important process that determines the quality of the color of the LCD panel depending on how precisely and uniformly this liquid crystal is dispensed. Therefore, the 32,000 ppr encoder, which has the highest precision in AC Servo, is also applied to this machine to increase the precision of liquid crystal dispensed. In addition, in order to bond the panel and the color filter, the glue must be uniformly applied to the color filter. If this glue is applied more on one side and less on one side, as you can see, the applied part is not straight. It is applied like a snake. In this case, the area of which the liquid crystal is placed changes, the amount changes when the area changes, and the color changes when the amount changes. In other words, constant liquid crystal dispensing and uniform application of glue are key to improving the color quality of LCD. From the conclusion, in the past, users used the AC Servo when dispensing this liquid crystal. In order to drop this liquid crystal from the perspective of the motor shaft, it is necessary to move to a high speed short pitch. However, if you use the AC Servo at this time, there is a high possibility of overshoot. Due to overshoot, the amount of liquid crystal was not dispensed uniformly, and the engineer was forced to tune the gain every time, and the cumbersome work continued. However, if you use FASTECH AC Servo, of course, the step motor will overshoot, but the amount is less than that of the AC Servo, and the overshoot amount is constant. Also, no gain tuning is required. On the other hand, since the amount of AC Servo is not constant and varies depending on the gain tuning, we propose to apply the AC Servo. But because of the customer's general perception that it also could not be a stepping motor when the AC Servo was not available, It took a year to suggest and do a test for replacing from AC Servo to Ezi Servo. This is the actual liquid crystal dispensing machine. It took a year to get an opportunity to test the AC Servo, but after the engineers actually tested the AC Servo, the AC Servo that was on the entire machine could be replaced with the AC Servo at once. You can see the AC Servo is installed here. I explained earlier that the glue must be applied to the color filter regularly. In this case, it is necessary to use a laser sensor to control the gap between the color filter and the dispenser to be constant. This machine shown in the picture is the machine that controls the gap between the nozzle and the color filter through a laser sensor. In order to dispensing a certain amount, the distance between the color filter and the nozzle must always be constant. In other words, since gap control to keep the distance between the nozzle and the filter constant is necessary, an expensive laser sensor is applied to this part. The color filter looks flat on the surface, but is curved. Nozzle must maintain the height between the vented color filter and apply to glue following the gap, just like this. The gap is 50 microns. For example, if the distance between the nozzle and the filter is 100 micron apart, you have to move 50 micron at a time. If this spacing is not constant, such as 50 micron, if the distance is far apart, the glue will be less applied, or it will be more applied if applied closer. This means that the distance between the nozzle and the filter is always constant in order to apply this glue evenly. For example, if your goal is to keep a gap of 50 microns, if the nozzle is 60 microns away, you will have to order 10 microns down. When commanded like this, the AC Servo goes exactly 10 microns. Also, if you are 40 microns apart, you need to change the direction of the motor because you have to up 10 microns. Even at this time, the AC Servo moves up to exactly 10 microns. In the case of AC Servo, of course, position accuracy and loose motion are good, but the possibility of overshoot is high. So if an overshoot occurs and the motor moves too much, the glue may not be applied evenly. There's even a risk of damaging expensive filters by contacting the nozzle and filters. The graph you see in the measurement of the response of the servo and the step when the servo and the step do up and down by 10 microns under the same conditions. As before, the nozzle was not gap controlled by following the distance from the color filter, but this time 10 microns were only up and down in the fixed position to see the difference in response between the servo and the step. If you look at the graph, the red graph is AC Servo. In the same case of 10 micron up and down operation, the AC Servo up and down 3 times at the same time. Of course, there is a gain tuning, but if you increase the gain, there is a possibility that the glass may be damaged due to overshoot. In order for the servo to move without overshoot, the gain cannot be raised, which will result in a slow response, so it is not possible to quickly up and down. In comparison, AC Servo up and down 9 times without overshoot at the same time. If you use AC Servo, it means that the speed of the machine is calculated to increase 3 times. For example, if the speed at which the glue is dispensed is 100 mm per sec, it will move 100 mm for 1 second, and if you use an AC Servo, the gap control, that is up and down, is done 3 times. So the point to be corrected will be once every 33.3 mm. However, since AC Servo does this up and down motion for 9 times at the same time, it will add 3 times even between 33.3 mm. If the AC Servo is used even within the same 100 mm due to the response which eliminates the overshoot, the late response will be calibrated sparsely as before. If there is another bend point of the glass is in between, the response will be slower to compensate for the gap. So what's happening if we increase this speed by 300 mm per sec, that is triple the dispensing speed? Because AC Servo does up and down 9 times as a result, it will correct the position same as the AC Servo did 3 times. This means that the machine speed is tripled. In other words, by changing one motor, it has tripled the speed of the machine, increasing actual machine productivity by 3 times. In other words, there are many machines where AC Servo can perform higher than AC Servo if the motor is well selected according to the machine. I will introduce a small actuator as the next application example. In the case of small actuator, there are many high-speed short-pitch motions that move short distance at high speed, which is the advantage of stem motors. And it is sufficient to apply AC servos instead of AC servos. So it is an effective market for cost-effective. As previously shown, in the case of a small actuator, all the torque of the AC servo cannot be used because the moving distance is short. And it is an application that can advantage of a stem motor with no hunching characteristic at the target position. Therefore, in the past, most AC servo were used, but many customers who know the advantages of stem motors use AC servo. Lastly, I will show you examples that AC servo actually apply, replacing AC servo to a small precision stage. This is Japan's Tsurugaseiki Gonio stage used for camera module alignment machine. You can see that AC servo motor is applied. In addition to Japan stage, you can see that the AC servo has been applied to the Mentor stage, a Korean precision small stage company. You can see that FASTECH's AC servo motor is applied to Taiwan's precision small stage.